Alright, now in this second video we're going to be basically discussing a simple circuit which I have drawn up here, and I'm not going to go into a whole lot of detail. We'll try and get you introduced to a couple of concepts that I think will help you to get going with your electrical understanding, try and get you sort of in the direction you need to go. First thing is, what do we have drawn here? Well, this is a electrical signal for a DC power supply. DC, that being direct current. The reason why we call it direct current will be much more apparent later on when we start discussing alternating current, but for right now, just realize that when a battery supplies voltage to something, that voltage has a polarity. The polarity comes in the form of a positive and a negative. Okay? In this particular schematic, the positive is flowing through two resistors, which I've drawn here. Those resistors are in series. In series meaning that when the electricity, the potential, is forced through the first resistor and it leaves that first resistor at this point here, it has nowhere else to go but to continue traveling through the second resistor that I've drawn here. You can envision all of this line that I've drawn here as some sort of conductor, either a thin copper wire, it could be a small aluminum wire, it could be a metal plate that everything's attached to, whatever. But ultimately the electricity has to flow from the positive side of the battery. It flows through the first resistor, through the second resistor, and back to the negative side of the battery. This signal, or this symbol, which I have designated down here, this one, keep this in mind. It's important you know this. This is referred to as ground, okay? And the reason why it's referred to as ground, I'm not exactly certain offhand, but what it is this is sort of designating a marker for us. This lets us know where our electrical potential, the voltage, remember, voltage is our electrical potential. That's how much push we have for our electrons to move through our conductors. And whenever you hit the ground, okay, in other words, once the electrons have flown through this resistor and then through this resistor, they're going to have exhausted all of their potential, all of their energy going through these two. Now you still have flow, okay? It's not that there's no potential left at all, but everything returns to this reference point, okay? And then it returns through the voltage source, which has to, you could look at it like a pump, okay? It's very similar to a pump moving water. Here your water is given all of the pressure, all of the force that it needs to go through the system. Here may be a couple of things that we use our water to do. So we could have a couple of minor loads coming off the water. It could be just a couple of sprinklers coming off a hose. You could look at this that way. And so what we're doing is we're pushing something here. It could be a couple of water wheels that are being turned in a circle to create some kind of mechanical motion. But ultimately what you've done is you've created this 9 volts. This is just a 9-volt battery like you've seen your entire life. You hook up one conductor to the positive terminal on that battery. So the larger of the two tabs on the top is the positive. You hook up this wire, you run it through resistor 1, resistor 2, okay, I'm going to label these R1 and R2, and they run back to the negative terminal of the battery. Okay, so you'll notice that in our particular circuit that I've asked you to visualize, nowhere is there anything that is actually ground. There's no official piece that you're hooking into the circuit to make this point happen. This is a designator that we're using so that you know where your potential has returned to its lowest point and needs to be ran through the voltage source again in order to gain more energy. You might ask yourself, what am I looking at with these resistors? This is a normal symbol for a resistor. It just looks kind of like a squiggly line. If I was to draw it really concise and really, the way it normally appears, you would see it kind of like this. Okay? But if you were to see one in real life, it would look like this. This is your resistor. Okay? I'm going to set it kind of right down here. That's what a resistor actually is. The way they fabricate these things is not important. You'll see them anytime that you open up any piece of electronic equipment. You'll see them in most times if you open up any type of larger electrical equipment. They're very common to be found in different things. They're used for a variety of purposes which have no bearing on what we're talking about now, but they're very cheap, and they come in a lot of different varieties. They come with a lot of different set points, a lot of different I guess you'd say resistances. The purpose of this thing is you put it into a circuit so that it will oppose the flow of current, and it has a certain amount that it will oppose the flow of current. It's not important that we get into that right now, just that you know it's there. Okay, I'll put that to the side. So these two resistors that I've drawn up are each 1.5, and this is the Greek symbol for omega. We're going to use it to say ohms. So what is this? Just as volts is used as our unit when we're discussing electrostatic potential, okay? Whenever we're talking about electrons flowing through a circuit, there's a certain amount of push, a certain amount of opposition trying to stop that current from flowing, okay? Electrons flow, and that's now what we call current. Current has a different unit. We'll get into that in a little bit. These ohms are the units that we use to designate resistance. How hard is it to push the electrons through this particular piece, through this resistor, or this one, or whatever else happens to be in your circuit? Lots of things offer resistance to flow. And so whenever we're talking about resistance, we'll be using the designator of ohms with the symbol omega. This will be your consistent source of identification for any value that you have for resistors. Now, it could come in the form of larger values such as kiloohms or mega ohms, or it could come in smaller values such as milliohms or even micro ohms. Most important thing is that you know that this is resistance. Now, when we get into discussing actual circuits, and which we'll do in the next video, we're going to talk about how the relationship between voltage and resistance and current works. Current is the third of the building blocks of ideas that we're going to be using to discuss electricity. So here's current. I'm going to write it down. And you could look at current almost like a water meter. If I was to install a meter right here, from this point, I got a little meter here, and I'm going to run all of my electricity through this particular meter now, and we're going to cut this part of the circuit out. Everything has to go through here. And we're going to keep track, just like on the pipe flow through a distilling unit or an odometer on a car. This is going to keep track of the flow rate, and we're going to draw an A because this is going to be called an ammeter, okay? This is an ammeter. And the reason why it's an ammeter is because current is measured in a unit called amperes. You would be more familiar, most likely, with the term amps. Shorthand designator commonly used to refer to current, okay? It's also a unit that is given with a capital A. This is our unit, just as our omega is our unit for our ohm, just as our capital V is our unit for our volt. A is our unit for our amps. So here we have a 9-volt power supply, and we're pushing a certain amount of current, electron flow, through two resistors, which have a resistance designated in a matter of ohms, using a potential that we've designated in volts from a battery. Okay? So this is a very brief, very simple explanation to a circuit. Remember, current is the amount of electrons flowing past this point or any other point where you happen to be talking about or analyzing in a circuit. Your amount of electron flow past that point per unit of time. So you can look at an amp as a number of electrons per second. That's what your current is. It's how many charge carriers, how many electrons am I moving past a point in my circuit for every unit of time. Okay, and again, those will come with our normal System International designators such as milliamps, mega amps, kiloamps, or microamps, or whatever, what have you. An ampere is a large amount of current. You usually will see either smaller units or just the amp itself when you're discussing things, but they do get larger. Resistance values can get extremely large, voltage values can get extremely large or extremely small. But this is your basic circuit here: couple resistors, a battery, things that you now have seen. You've seen a resistor, you've seen a battery, and in our next video we're going to talk about how to solve this circuit to figure out how much current do we have flowing through this circuit, knowing that we have a 9-volt DC power supply, knowing that we have two 1.5 ohm resistors in the circuit. How much current can we expect to see when we read this ammeter? And that's what we'll get into in the next video.